Okay guys, so this is the orders bootcamp, and this is also going to include a bit on Arrhenius. So what you need to do is have a look at this, try and get it in your head, and then from memory, and that's the important bit, it has to be from memory, try and copy it down, and then repeat, repeat, repeat. Obviously checking your answer every time. So we're going to do it 5 minutes per page. Starting from now, off we go. Halfway there, guys. Less than a minute to go. Try and get it out one more time. Okie dokie guys, so on to first order. So a little point out to make out that thing in red at the bottom, it has to pass through the origin. That's at 0, 0. That's because when the concentration is 0, the rate of reaction must be 0. You can't have a reaction if you don't have the reactant, right? Another little thing about calculating half-lives, when you do calculate the half-life, you should calculate at least the first 3. You can't get a reliable trend unless you've calculated at least 3. And when it says half-life is constant, obviously due to human error and maybe experimental error in the results, you might not get your first 3 half-lives as exactly constant, but they should be almost practically the same. Almost there guys, a minute and a half to go, getting close. Okay guys, so on to second orders. So you'll notice the second order conch time graph looks very similar to the first order. This is why we should be figuring out the half-life in order to determine the difference. And again, on the rate conch graph, if the concentration is 0, the rate's going to be 0. You need reactant to have a reaction. And so this must also pass through the origin. Just 2 minutes to go, almost there. One minute remaining. Okay guys, done really well. I thought give your hand a little bit of a rest and you can watch this video of hedgehogs dressed as sharks. Oh, aren't they sweet? Oh. Okay, so on to different ways of finding K. So if you have a first order reactant, K is equal to the natural log of 2 divided by the half-life. Also, if you've got a reaction with an overall order of 1, so rate equals K multiplied by the concentration of A to the power of 1, then the rate conc graph of that chemical, if you take the gradient is K. And then finally there's the table method, where they give you lots of different experiments and they change the concentrations of the chemicals and look at what effect that had on the initial rate. If you're going to try and explain how that table tells you K, use the sentence below. Between experiments blank and blank, the conc of blank increased by a factor of blank. This increased the initial rate by a factor of blank. Therefore blank is blank order. That last number 3, that sentence in particular, is important to remember. Otherwise, you can waffle on for half a page trying to explain what you're trying to say and not actually say it. So by just memorizing that, literally all you need to do is fill in the blanks. Less than a minute left. Okay, try and finish off the one you're doing. Okay, and on to the clock reactions one. So you will probably want to stop the video now and take a 20-minute, half-hour break, go off and do something else. We don't want your brain melting out your ears and you've been doing 20 minutes of boot camp already. That's a long time. So I would stop, take a break, and we'll come back and do the last two in a bit, and you can just restart the video. Welcome back. So this is clock reactions. This is where we're going to use time and some sort of visual change in order to find K. So it's just another way to find the rate constant. And what we do is we measure the time taken for a visual change. Now in your PAG you've done the disappearing cross. If you remember, you had thiosulfate and you timed how long it took for the cross to disappear. We then do this for several different concentrations. We then do 1 divided by the time and 1 over the time taken for the cross to disappear or for some other visual change to occur. This is the rate of reaction, only now it will have the unit seconds to the -1. If we then do a graph of 1 over time versus concentration, the tangent to that graph, and therefore finding the gradient, is K. If you wanted to find K for the initial start of the reaction, you would draw the tangent at the origin. Incidentally as well, another way of measuring the time taken would be for a coloured solution to reach a certain intensity, so like the deepness of the colour. And we could use this by doing a colorimeter, which is just a machine which measures, it's quite a fancy machine, and it measures the intensity of the colour of a solution. So that would be an alternative way to measure the time taken for a visual change. And there's others too. Just a minute left to go. almost there. 10 more seconds. Let's finish off the one we're doing. Okay, so on to our final one. So this is the Arrhenius. So what I've done is I've taken the Arrhenius equation and I've put it into the y equals mx plus c form. This equation here is on your data sheet, only on your data sheet these two are joined together, the 1 over t and the minus ea over r. I think the way I've written it is the best form, because then it is truly in the y equals mx plus c form. So in this form we can see c is the natural log of a, and therefore the y-intercept is the natural log of a. We can see m, which is the gradient, is minus the activation energy divided by the ideal gas constant. And don't forget, your gradient will always come out as a negative number. So the negative gradient will cancel that negative there. And that's because activation energy is always positive. I should say as well, sometimes the way the graph will be drawn in the exam, your line will not pass through the y-intercept or the y-axis, and therefore you cannot use y-intercept equals the natural log of a in order to find a. If that's the case, pick any point on your line of best fit, so for example this point there, read off your natural log of k, sub it in, read off 1 over temperature, sub it in. Your gradient is minus Ea over R, so you'll now have all the information you need to rearrange and find A. Okay guys, so let's do 5 minutes from now. Last one, almost there, off we go. If you struggle with the Arrhenius as well, don't forget I do have a Brady Explains on it. And don't forget to like it. One other thing to be aware of with the Arrhenius equation is it is new to the new syllabus. So depending on when you're watching this, there probably isn't that many past paper questions, if any, on it. And so what you're really going to want to do is use those questions from the book, use this video, use the Brady Explains to really get it stuck in your head. Okie dokie guys, 10 more seconds. Okay, really well done. So, the thing to do now, as always when you're boot camping, well done for completing this one. The best way to get the most long-term learning from this and to really make it stick in your head is to do this again in 3 days' time, maybe a little bit quicker. So maybe even, rather than taking half an hour, let's take 20, 25 minutes, and then do the same thing again in a week's time. So do it in 3 days' time, do it a week after that. That's what's really going to make it stick in. Okay, thanks a lot guys, have a nice day.